So, hi, this is Zoe's Kitchen, and this is the moments question that I've given you, which is a tricky one because it involves tilting. So, hopefully, you can see that, and I'm going to have a go at working it out so you can see how I think. So, here's my uniform plank. And uniform already tells us something about where to draw on its weight. It weighs 120 newtons and has a length of 3 meters. So I can immediately start my diagram. I can copy their diagram, or you can draw on theirs. I'm going to go large. So here's my plank. I know it's 3 meters long. I know it's uniform, so that means its weight is going to act right in the middle here. So I'm going to draw that force on already. 120 newtons. So it's the weight that's been given, not the mass. So that is all I need to put in there. Now if I copy my diagram here, already we can see we've got A, B, C, D with pivots at C and D. And C is 1 meter from A, so I'm just going to put that in. So A, 1 meter to B, and there's a support or a pivot there at B. C, oh sorry, that's C. We're going to have another support here somewhere, that's D. And the other end of the rod or beam is called B. Okay, and we know some of the distances here. So I know this distance here is 1 meter, that's on the question. I also know that the distance between C and D is X meters. And the whole distance is 3 meters. Let's have another look at that. So that means the centre of gravity, the weight, is acting exactly halfway along there, which is at 1.5 meters. So 1.5 meters along. And that means that this is also 1.5 meters. So the real key to this is getting as much information onto your diagram as possible. I've got what's on the question, but I've also put on one of the forces already. You can always use another colour for the forces. Okay, so I think we've got everything from this top part. We've got the weight of 120 newtons, the length 3 meters, the plank is resting in equilibrium on C and D. AC is 1 meter, CD is this X, and the reaction of the support on the plank at D has magnitude 80 newtons. Okay, we haven't got that in there yet. So let's put that in there. We have been given, somehow they've measured at point D that the reaction, which is just going to be acting upwards, there's no weird angles in this question, that there's a force of 80 newtons has been measured there. The weight, we've chosen to place it as if it's acting all in one place in the middle here. So it's a little bit further away here. So there isn't any weight supposedly acting through this point, which is a bit weird. But that reaction and the strength of the beam, so the beam's kind of transferring some of that energy in its structure, some of that force is being carried by the structure of the beam, and hence this support acts upwards here. So that's everything that we've got so far. Now don't worry, we don't know X. There is a possibility that this X, if it was very small, then actually the weight would be further to the right and the pivot might be here. But I can see a little bit of a problem with that, in that there would be tilting going on. So if my centre of gravity was outside of both the supports, if we had a support here that the whole thing would tilt. So I'm going to show you that with a ruler and 2 pens. So here's my 2 pens. Here's my ruler. Now this is our situation. We're looking at a rod sitting on top of 2 supports. And if I move this support closer and I have my centre of my ruler, I'm going to have to set it upside down, it's a bit bent, is further over. So the middle would be, for this ruler, 75 millimetres long. There it is. If it's further to the right than both supports, of course this side's going to touch down on the ground. So it must be the case that somehow the centre of the rod is sitting in between the 2 supports. Otherwise we would not be resting in equilibrium. We would be resting with one end on the ground. So you can always get your ruler out and play around a little bit if you need to check this stuff out. Okay, so what we haven't got on our diagram yet because part A already asks, show that x equals 0.75. And by the way, anytime you think, right, I can crack on with this, just pause the video and get on with it and see how we compare. So the next stage I'm going to go to is making sure I've got all the other forces on here. Now there aren't many other forces. In fact, there's only one that I've missed. You can probably work out which one it is. I've got a reaction here. I've got the weight here. There's no other weights. Nobody's sitting on this seesaw. So the only other force is at C, that there is a reaction there. We've not been told that one. I'm going to call it R. I might even label it RC so that I know what I'm talking about. So this is the normal reaction of the support at C. So I'm going to always put on all our forces in another colour if you like. Try not to use arrows, similar arrows for things like acceleration and velocity. Just stick to forces at this stage. So we are in equilibrium. Everything is stable. Now what that means is a couple of things. It means that it's not moving up or down or side to side, but it's also not pivoting, it's not twisting. So there's no turning moment on this system. So what that means is I could potentially have still got my tools. So in equilibrium, I've got some tools. I could say that we are horizontally no resultant force. Now that should be fairly obvious because on our diagram there isn't anything moving this side to side, so horizontally we're in equilibrium. Also up and down, so in a vertical direction there is no resultant force. Now, I don't know if I'm going to use that for this first part of the question, but let's have a quick look at our diagram again. What that means is I can resolve this. All of those vertical forces must balance out. Otherwise the thing would fall down or it would move up. So can you see a simple equation forming there? The 2 upward forces, the 1 downward force. Yep, I can see where I'm going with that. It's going to be my reaction at C plus my reaction at D, which is 80 newtons, are going to balance out that 120 newton weight. So down forces and up forces just balance. So actually I already know what RC is. I've not been asked to find that, but never know, it might be useful. So I can take away the 80, and this must just be 40 newtons. Okay. So the last thing in equilibrium that we know is, of course, this is a question about moments, and much as you'll get some marks for resolving, we have our turning force. So no resultant turning moments. So doesn't mean there are no moments on here, it means the resultant is zero. So it just means they balance. So we can form an equation about that. So what's key with moments, so if we look at our diagram, is we can use any point here as the pivot. None of these points are pivoting, it's not moving around any of the points. So if I have an unknown in there that's kind of missing, then that's a great point to take moments about, because I can ignore any forces that are acting at that point. So I could, and you'd still get the answer, you could take moments about A, you could take moments about C, D or B. So try a couple of points, see how you get on. You might well find that you can get there through another route. So there's not a wrong and a right here. The one force that we aren't given is this RC, but we've already worked that out. So it was really easy to work out what RC was. So we could always take moments anywhere really, and we could work out what that is. But if we hadn't worked that out, that would be a great spot to start, because when we multiply this force by its perpendicular distance from C, its perpendicular distance is zero. So it's not having a twisting effect about this point. So what that means is we only have to look at these other two forces. They are the ones that are going to affect whether this pivots at this point. So we just have two forces to look at. So and they're going to balance each other out. You can see one is trying to move it up this way, and this force down here is trying to move it the other way. So they are working against each other in terms of pivoting. So remember, the moment is the turning effect, and that is the force times perpendicular distance. Everything's perpendicular in this question, so that's something good. So on the one hand we have an 80 Newton force, and its distance from C is x meters. So C. So if I'm taking moments about C, I might use C under a little turning moment. So we've got 80 times x is the force times the distance, and that's completely balanced out by, so look, the weight. And how far away is the weight? So just give you a second to figure that out. How far is it from C? This is not too horrible because we've got 1 metre here. 1.5 metres is the whole distance. So this little distance in here is the 0.5 metres. Okay, so we've got real whole numbers going on. So we've got 120 newtons times 0.5 metres. So that's how I'm going to find my x. That's why I don't get a lot of marks, I just get the marks for a nice clear diagram. So 80x equals 120 times a half, 60. So x turns out to be 60 divided by 80, which is 3/4, 0.75 metres. Okay, so that's part A. Part B coming next.